Okay, so today we are looking at power series solutions to differential equations. We are looking at power series solutions to differential equations. So we have seen that differential equations can be evaluated in different ways using different methods, depending on their nature. If you're looking at the first order differential equation, you can evaluate and find the general formula using, when you're separating by variables. You're looking at the second order differential equation, you can evaluate it using the integrating factor. So now we are looking at another way of finding a series of solutions to differential equations. So now we are saying we want to use the power series. Series to find solutions to differential equations. So how do you go about then? So even here we need to look at the nature of the differential equation to be able to find the series solution for that differential equation. So in our case, if we are given a differential equation of this form, p of x y double prime plus q of x y prime plus r of x y is equals to 0. So this is a homogeneous second order differential equation. So with this one, we can easily see that p of x, q of x, and r of x are these are non-constant coefficients. So this is, if you're given a differential equation and you have non-constant coefficients, this is one way you can see that you can apply the power series solution to solve for the differential equation. So if you have your coefficients as being non-constant, so they can be functions. These are functions. Your coefficients are functions with respect to x, right? They are functions of x. So given this format, you can find your series solution. But then in order for you to find the series solutions, we are saying there should exist a point x is equals to x naught, which is called an ordinary point, provided both qx over px and rx over px are analytic at x is equals to x naught. We are saying there exists a point x is equals to x naught, which is an ordinary point, provided both qx over px and rx over px are analytic at that same point. What do you mean by this? We are saying these two expressions, they have Taylor series around this point. And remember, with a Taylor series is also a power series. Because the Taylor series can be represented as the sum from n is equals to 0 to infinity of f of n a over n factorial x minus an. So this, you can see that this a power series is also it's also a Taylor series is also a power series. So we are saying these are analytic at this point. We are saying when both qx and px and rs over px are analytic at the point x is equal to, we're saying they satisfy this condition. So now, in order for you to solve this, in order for you to find the solution, we are going to assume that the non-constant coefficients are polynomials. We are going to work with non-constant. We are saying the non-constant coefficients are polynomials. We are polynomials. In this video, I'm going to solve questions whereby the non-constant coefficients are polynomials, which means if they're polynomials, that means, because here p of x is a denominator, that means p of x shouldn't be equals to 0, right? That means p of x shouldn't be equals to 0 since it's a denominator. If you evaluate this, you divide everything by p of x, obviously you're going to get y double prime plus q of x over p of x, y prime plus r of x over p of x prime is equal to 0. So I'm saying, if we are assuming that the non-constant coefficients are polynomials, I'm saying p of x shouldn't be equal to 0. So that's what we're going to do here. So at this point, we are saying this is a very important statement. There exists a point, which is an ordinary point, provided both these two expressions are analytic, which means these 2 points, they form a Taylor series at x is equals to x naught. If we don't have an ordinary point, we have a singular point. So the basic idea in finding a series solution to a differential equation is to assume that we can write the solution as a power series in this form. We can write the solution as a power series in this form. Y of x is equals to the sum of n is equals to 0, x an x minus x naught n, right? Remember where x is equals to x naught. And we can also evaluate this as yx. We can evaluate this as yx is equals to the sum n is equals to 0. Or we can evaluate this as if x naught is equals to 0, we can evaluate y of x is equals to the sum n is equals to 0 to infinity an of x to the power n, right? So we are saying at this point, when finding the series solution to a differential equation, we can assume that we can write a solution as a power series in this form, right? So this is going to help us to determine the value of an, and we are going to form what we call recurrency equations, which are going to help us to evaluate the coefficients of this series. You can also break down this power series into a naught plus a 1x plus a 2x squared plus a 3x cubed plus a 4x to the power 4 plus it continues, right, to a n x to the power n, isn't it? So this is the same thing. So now I'm going to show you two ways of how you can actually determine a series solution of a differential equation evaluated at an ordinary point. So our first example is going to be, okay, let's start with example 1. So we are given a problem. We say we are tasked to determine a series solution of a differential equation about your ordinary point x naught is equals to 0, and the differential equation is d squared. I'm just going to take the simplest form for now, plus y is equals to 0. So we are given this differential equation. They are saying find the series solution at this point. So what do you do? So here, first of all, we need to note something. You need to note something that your value for p of x is equals to 1, because p of x is here, right? So p of x is equals to 1, which means now we are looking at a general solution for the power series. A general solution, we said, is going to be the sum of n is equals to 0 to infinity a n x to the power n, since x naught is equals to 0. So here x naught is what? It's 0, because they said we are evaluating at an ordinary point where x naught is equals to 0, which means here we have 0. That's why we are getting this solution. So now allow me to write this one as x is equals to x naught plus a1x plus a2x squared plus a3x cubed plus a4x to the power 4 plus a5x to the power 5 plus it continues, right, till infinity. And then now this is what I'm going to do. In order for me to determine the series solution for this equation, I'm going to differentiate this expression twice, and then I'm going to substitute in the differential equation that I'm given, and then I'm going to solve and simplify. So first of all, you need to find the first derivative of this. It's going to be equals to what? a1 plus 2a2x plus 3a3x squared plus 4a4x cubed plus 5a5x to the power 4 plus it continues, right? And then y double prime, the second derivative of this is going to be 2a2 plus 6a3x plus 12a4x squared plus 20a5x cubed plus it continues, isn't it? So now I have the value of y. I found the first derivative, second derivative. So I'm just going to substitute into this equation. Right, we're given this equation. So let me just highlight something. Y double prime x is the same thing as dy dx in our case, and also y prime is the same thing as dy dx. So if you are substituting this, which means here I'm going to substitute this expression. So this is going to be 2a2 plus 6a3x plus 12a4x squared plus 20a5x cubed plus, you need to show this. You need to show these dotted lines to show that it's a continuous series, right? So, and then this is going to be plus y. What is y? Y is our initial series here. This is our y. So our y is going to be a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the power 4 plus a5x to the power 5 plus it continues. So now this is equals to 0. So now I've rewrote this second order homogeneous differential equation in this series form. So then from here, what I'm going to do, I'm going to collect like terms in terms of my variables. So I'm going to collect like terms in terms of x squared, x cubed, x to the power 4, x to the power 5, etc. Oh, sorry, I made a mistake here. So this is x squared, this is x cubed, isn't it? So, okay, which means here I can also go as far as, just for consistency, since I have went as far as x cubed this side, here I'm also going to go as far as x cubed. It depends on how many terms you can work with. If you can work with more than these terms that I've used here, you can also work x to the power 5, x to the power 6. But like, let me just go with x to the power 3, x cubed. This is equals to 0. So let me collect like terms. So this is a constant, this is a constant. So I'm going to have 2a2 plus a0, right? Plus, and then I'm looking at the coefficients of x. So it's going to be 6a3 plus a1x plus, I'm looking at the power, at the coefficients of x squared is going to be 12a to the power 4 plus a squared, a2 x squared. It's 12a4 plus a2 x squared. And then I'm looking at the coefficients of x cubed. I'm going to have 20a5 plus a3x cubed. Obviously this continues, isn't it? This is equals to 0. And then from here, then you need to make an argument here. So we are saying when we're adding these terms, they have to give us 0. And in order for you to get a 0, we are saying the coefficient of x should be 0. The coefficient of x should be equated to 0. So what does this mean? This means 0 plus 0 times x plus 0 times x squared plus 0 times x cubed, etc. You have to get 0. So which means these are equated to 0, right? So you're going to have 2a squared plus a0 is equals to 0. We are also going to have 6a3 plus a1 is equals to 0. We are also going to have 12a4 plus a2 is equals to 0. And then you are going to have 20a5 plus a3 is equals to 0. And then from these ones, you are going to make a2. From here, I'm going to make a2 the substitute of the formula. So this is going to be equals to a minus a0 over 2. Here, I'm going to make a3 substitute of the formula. So I'm going to have a3 is equals to minus a1 over 6. And then here, the same thing, I'm going to make a4 substitute of the formula. So this is going to be equals to what? This is going to be equals to minus a2 over 12, right? but we know that A2 is what? A2, this is A2, this is our A2. A2 is minus A naught over 2. So we can simplify this to be minus 1 over 12, and then A2 is going to be what? It's going to be this, which is minus A naught over 2. Then this simplifies to what? This simplifies to A naught over 24. This means A4 is equals to A naught over 24, right? So from this point, we are going to over 24. And then now, the last one we are saying, we are going to make A5 the substitute formula. So A5 is equals to minus A3 over 20. But we know that A3 is equals to minus A1 over 6. So this is minus 1 over 20. Instead of A3, we are going to have A minus A1 over 6 here. So we can further simplify this to what? To A1 over 120, if I'm not mistaken. So now A5 is A1 over 120. So now you have represented A2, A3, A4, A5 in terms of, we have represented these coefficients, these constants in terms of A naught and A1, right? So now we are going to come back to our original series. We say A naught plus A1x plus A2x squared plus A3x cubed plus A4x to the power 4 plus A5x to the power 5 plus, it continues, right? So from here, we are going to substitute these coefficients that we've just derived. So yx is equals to A naught plus A1x. And then now we have A2 here, but we know that A2 is what? It's minus A1 over 6. So here we're going to have minus A1 over 6 x squared. And then A3 is what? A3, it's, A2 is minus A naught over 2. A2 is minus A naught over 2. So this is, we're going to have A2 is minus A naught over 2 from this expression, and then A3 is going to be minus A1 over 6 x cubed, and then A4 is what? A4, we said it's A naught over 24 plus A naught over 24, and then we said A5 is what? This is x to the power 4. This is x squared, And then we are saying A5 is what? A5 is equals to positive A1 over 120 x to the power 5 plus, this continues. So now let me just rewrite this. So we have transformed our series into A naught and A1. So A naught plus A1x minus A naught over 2 x squared minus A1 over 6 x cubed plus A naught over 24 x to the power 4 plus A1 over 120 x to the power 5, and then this continues. So now I'm going to factor out A1 and also factor out A naught, and this is going to be is equals to if I start with a naught, factor out a naught, so all the terms that have a naught, this is, if I factor out a naught, we're going to have 1 here, and then we're going to have minus, we're going to have, this is, if I factor out a naught here, we are going to have x squared over 2, and then you're factoring out a naught here, we're going to have plus x to the power 4 over 24, right? Plus it continues, isn't it? And then this is plus, factor out a1 here, we are going to have, if you are factoring out a1 here, this is going to be x, and also if you are factoring out a1 here, it's going to be minus x cubed over 6, and factor out a1 here is going to be plus it's going to be plus x to the power 5 over 120 plus, obviously the series continues, right? And then now you have represented the series solution of this differential equation into, this is the solution, this is the series solution of the second derivative of plus y is equals to 0. So this is one way of finding the series solution of a differential equation. So now let me use another method whereby I'm going to look at the recurrency equations. I'm going to form recurrency equations in order for me to get the values of the coefficients. So solving the same problem, let me say, or I'm using another method. So I'm given d squared dy dx squared plus y is equals to 0. We are still looking at the power series solution for differential equation, but there's another way you can solve this equation. So now remember, we are saying we are evaluating this where x naught is equals to 0, right? So in order for us to evaluate this problem, we are saying we assume that there's a solution in this form: y of x is equals to the sum n is equals to 0 to infinity of a n x to the power n, isn't it? So this is the first step. So here we do again take the first derivative. For this one, we are going to have what? The sum n is equals to naught, and we're going to have a n x n minus 1, isn't it? And then take the second derivative of this one. We are going to have the sum n is equals to 0 to infinity a n minus 1 x n minus 2. I'm using the power rule of finding derivatives, right? When you're given y is equals to x squared, y prime is going to be 2x, and then you minus 1 here, it's 1, so it's 2x, just simple derivatives. So now I found the first and the second derivative for this one. I found the first and the second derivative using the power rule. So, and we come back and substitute in this equation. We're coming back and substituting in this equation. So in this equation, so we are going to have the second derivative n is equals to, we are finding the first derivative here, so this is going to be evaluated starting n is equals to 1, and then if you're finding the second derivative, it's going to be evaluated at n is equals to 2, and if you're finding the third derivative, it's going to be n is equals to 3, etc, etc. So now if you're finding the nth derivative, it's going to n is equals to n to infinity. So now we are going to substitute from this equation. So we're going to have n n minus 1, x n minus 2, right? This is the second step, plus y, plus, what is our y? This is our y. So plus the sum of n is equals to 0 to infinity of an x, and this is supposed to be 0. So from here, there are certain things that you have to look at. First of all, you can see that this series starts from n is equals to 2. This one starts from n is equals to 0, and also the power of x is different. This one is n minus 2. This one is n. So in order for you to work this out, you need to make sure that the exponent of x is the same for both series. How do you make sure of that? Which means for this one, for the first series, the first term in this equation, make sure that you, where there's n, you add, where there's n, you substitute by n plus 2. Substitute by n plus 2 in this first one, so that all of the terms have the exponent of x to n. So this is going to be n, the summation when n plus 2 is equals to 2 to infinity. It's going to be a n plus 2, n plus 2, and if you add n plus 2 here, you're going to have n plus 1, and this is x, n plus 2 minus 2, and then plus this, and then I'm now looking at this, evaluating this term. It's just going to be a n x n equals to 0. So remember, I'm saying I want to make sure that the exponential of x is the same. So I'm choosing to keep x to the power n my main exponential. So I have to change this one, x to the power n minus 2, to be x to the power n. How do I do that? I make sure that at this term, I evaluate, I substitute, where there is n, I substitute with n plus 2. So now if I simplify this, so if I take this to this side, it's going to be, the summation is n is equals to 0 to infinity, a n plus 2, n plus 2, n plus 1, x, this is going to be n minus 2, 2 minus 2 is 0. So plus x 0 an is equals to 0. So in this case, we have changed the exponent of x to be n, right? And then also automatically these two summation series, these two summations, they are evaluated starting from n is equals to 0, both of them. But it is not, most of the cases you'll find that you need to also change the initial evaluation of the summation, just that maybe they don't start from the same point. You need to make sure that they start to the same point. That's the second step. After evaluating the exponent of x, you need to make sure that the summation, they start at the same point. But here, by default, they are starting at the same point. So this is okay. So from here, what do? You're going to factor out the summation and xn because they are the common term. They are a common vector. So you're going to have n is equals to 0. We're going to have a n plus 2. So we're going to have n plus 2 and n plus 1, and this is going to be plus n a x to the power n, and then obviously I factored x to the power n out, which is equals to 0. So now I have this series, so I have this equation. So now I'm saying this equation is equals to 0, and we make the same argument that we made before, that this can only be 0 if the coefficient is 0, right? So this can only be 0 if the coefficient is 0. So in our case, this is our coefficients. This is our coefficients here. So this is going to be 0. So n plus 2 n plus 2 n plus 1 plus an. Oh, sorry guys, this n shouldn't be here because it was factored out. So it was factored out, shouldn't be here because I factored these two n's out. So this is going to be an. This is supposed to be 0 in order for this entire equation to be true. So now I'm going to make an plus 2 the substitute of the formula. So an plus 2 is equals to minus an over n plus 2 n plus 1, right? So then from here, I'm going to evaluate. Remember, we are saying from n is equals to 0 to infinity, right? Which means n is greater or equals to 0. That means n is equals to 0, 1, 2, 3, 4, 4, 5. It continues till infinity, isn't it? So whenever we substitute the value of n here in this equation, we are going to find the value of a. So we call this equation the recurrency. This is the recurrency relation. We call this the recurrency relation. So this is the equation that we're going to use to find the values of our coefficients for the power series. So here we first of all we're going to say when n is equals to 0, so we're going to have a 0 plus 2, which is just this is going to be 2 here. So a2 is equals to, where there's n we put 0, so this is minus a naught over, where there's n in the denominator you put 0, so it is going to be 2 times 1, right? And then when n is equals to 1, we are going to have, so here we're going to have 1 plus 2, right, which is 3. So you're going to have a 3 is equals to, here where there's n you put 1, so this is minus a1 over, where there's n in the denominator you put 1, so it is going to be 3 times 2. And then n is equals to 2. This is going to be what? This is going to be a5, which is equals to minus a2 over, which means where there's n here you put 2, so it's going to be 4 times 3. But remember, we do have the value of a2. This is the value of a2, so we can further simplify this as minus 1 over 4 times 3 is what? 4 times 3 is 12, and then the value of a2 is what? It's minus a naught over 2, which is equals to a naught over 24. And here it's a minus a1 over 6. Here we've already evaluated this is a naught over 2. So now from here we can rewrite. Remember, we assume that our series is a naught plus a1x plus we have a2 x squared plus a3 x cubed plus a4 x to the power 4 plus we are saying hopefully I still have the file. Okay, so we are saying we are continuing plus a5x5 plus this continues. So from here again, now we have generated our coefficients, right, using the recurrency relation, so we are going to substitute here. So yx is equals to a naught plus a1x. So now a2, what is a2? A2 is what? A2 is equals to minus a naught over 2. So this is minus a naught over 2 x squared, right? And x squared. And what is a3? A3 is equals to minus a1. A3 is equals to minus a1. A3 is equals to minus a1. Let me just erase this. A3 is equals to minus, this is supposed to be minus a1 over 6, that's a3. So this is x cubed. A4 is what? A4, did we evaluate a4? From this equation, did we evaluate a4? No, this was supposed to be a4. This was supposed to be a4 because 2 plus 2, because we're saying n is equals to 2, so 2 plus 2 is 4. This is a4. So we need to evaluate when n is equals to 3, which means when n is equals to 3, we're going to have what? A5 is equals to, where there is n here, so we're going to have minus a3 over, when n is 3, you're going to have 5 times 4, right? But we know that a3 is what? This is a3 is minus a1 over, so minus, this is equals to minus 1 over, this is 20, and we know that a3 is minus a1 over 6, so this is going to be a1 over 120. So here a5 with respect to a1 is what? It's plus a1 over 120 x5. So from using the same principle, you are going to factor out a naught and list all the terms for a naught, and then plus factor out a1 and list all the terms of a1. So finally our series solution is going to be, so we are saying we are looking at a naught, so listing all the terms of a naught. This is going to be, this is a1, this is a1, and then for a4 it's a naught, so a4, I keep on making mistakes. So a4 here, a4, this is a4 is this, so plus a naught over 24, and then a5 is this, which is plus a1 over 120. So a naught is going to be 1 minus, this is the 1 comes from here, minus, if we factor out a naught here, we are going to have minus, we already write the minus x squared over 2, and then a naught here is going to be plus, this is x to the power 4, this is x to the power 5, this is going to be x to the power 4 over 24 plus, it continues, then plus, we factor out a1. If we factor out a1, we are going to have x. If we factor out a1 here, we're going to have x. If we factor out a1 here, we're going to have minus x cubed over 6. If you factor out a1 here, you're going to be left with x to the power 5 over 120 plus it continues. So as you can see, now this is our series solution. Again, this is our series solution. As you can see, this one is the same as this solution that we got earlier. It's the same as this one. So these are the two methods that you can use. You can use this one where you're going to get a recurrency relation equation. Once you get the recurrency relation equation, you generate the constant, the coefficients with respect to a0 and a1, and then you substitute them in the general form of your series solution, and then you simplify to get this. Or you can use the first method whereby right off the bat we just expanded this series solution, the series into a0, a1, a2, a3, a4, a5, just like here, and then you find the first derivative of the expanded series and the second derivative of the expanded series, and then you substitute in this differential equation. Once you substitute, here we substituted. Once you substitute, you group the terms according to the variable x. So we group them according to x squared, x cubed, etc. And then in order for this equation to be true, we made a statement or an argument that the coefficients of x, all values of x should be equated to 0. So the coefficient of x is 0, the coefficient of x squared is 0, the coefficient of x to the power 3 is 0, the coefficient of x to the power 4, etc. is 0, right? So if you add those 0 terms, we're going to get 0. So if that's the case, which means this is equals to 0, this is equals to 0, this is equals to 0, and this is equals to 0. So if you have formulated these equations and then you make a2 the subject of the formula, a3 the subject of the formula, a4 the subject of the formula and a5 the subject of the formula, but then you have to solve them such that from a2 to a5 you represent those coefficients with respect to a0 and a1. Once you get the coefficients with respect to a0 and a1, you come back to the initial series, and then you substitute where there's a2, a3, a4, a5. You substitute with respect to a0 and a1, and then once you have substituted, as you can see here, and then you need to group them. So you factor out a0, you list all the terms for a0, you factor out a1, you list all the terms for a1. So that's your solution for this differential equation. So in another video we are going to do another equation whereby we are pretty much doing the same thing, finding the series solution around the point x naught is equals to something for any differential equation. And remember, we are saying in order for us to use this assumption, in order for us to find the power series solution for differential equation, px, qx, and rx are non-constant coefficients. And since I said in this video we are looking at these non-constant coefficients, they are polynomials, so which means p of x shouldn't be equals to 0. So we are going to do more questions on that, and I'll be using the first method to solving those equations, but you can also use the second method. I was just showing you so that you can see there are many ways depending on the book that you'll be using, or whatever reference that you're using to study differential equations. so that you can understand the different types of method of solving the same equation. So this is about it. This is it about this video. So in the next video, I'm going to solve another equation, another differential equation using this method, the power series solution method, so that we can see how we can evaluate it. So thank you for watching.